Describe your area of interest in Yellowstone.
My area of interest follows my background. I have degrees, a PhD in geophysics and degrees in geology, and I studied mathematics and computer science. So my areas of interest in Yellowstone have been focused using earthquake studies, seismology, I'm a seismologist, but they move into the areas of deformation using global positioning systems. They move into the areas of understanding the dynamics and the chemistry of the system, and I integrate these together to solve a single problem. That is, I never just use seismology to attack a problem. I rely very much on the geologic history that's been well documented in Yellowstone. I rely on the geochemistry that other people have done, because we have to understand the one big basic thing is heat. It's a very high heat flow area because heat's coming off of a young and active magma reservoir. That heat leads to earthquakes, the heat leads to deformation, the heat leads to, of course, heating the ground that create the geysers, fumaroles, and hot springs. And so it's this roughly 6 gigawatts a year that come out of the earth from Yellowstone, enough to electrify a modern city. That is kind of the basic primeval feature that drives and is responsible for the other components.
What excites you about working on Yellowstone topics?
I've gone back now for 50-something years, and I'll be honest, every year we're discovering something new. Either the caldera is going up or it's going down. We've had big earthquakes, we've had interactions of earthquakes with geysers or things. And it's always finding out that you're seeing processes that are active today. Many geologists in their careers work on rocks that are millions and billions of years old. I like to work on Yellowstone because what's happening is real time, it's today. So it's real-time geology. And that's what makes it exciting for me, is to look at the processes we can develop from studying Yellowstone and then apply those processes to other places in the earth where there's volcanoes, where there's big faults and earthquakes. But Yellowstone truly is a window into the Earth's processing. It's really an active geologic laboratory, and the laboratory's alive.
How did you get hooked on earth science?
I was off studying mathematics or physics or something at the time at Utah State University, but as I got more and more into these topics, I got more and more interested in earth sciences. And then in 1959, we had the occurrence of the magnitude 7.5 Hebgen Lake earthquake just on the west side of Yellowstone. And we went up immediately as students and faculty, and I had relatives there, to see this giant earthquake. Well, it turns out it killed 28 people. It's the biggest normal faulting earthquake that's occurred in historic time in the basin and range. At the time, I'd been changing the seismogram records at the university to help pay for my little scholarship. And when I saw that earthquake, I said, wow, that's what I want to study. And that coupled back with my experience in Yellowstone, trying to understand how all that heat was being manifest. That was, I said to myself, did the Hebgen Lake earthquake have anything to do with this Yellowstone volcano? And that really turned me into taking a degree in geology, a bachelor's degree with studies in math and computers at Utah State. And that moved me on into geophysics following my master's degree. And that's where I've been ever since.
When did you begin studying seismology in the park?
Following my military career, came back, finished with my PhD. Then I started thinking about Yellowstone again. Nothing had been done there in the way of geophysics. So I started installing portable seismographs all around the park different places for different periods of time for about 2 to 3 years. And we mapped out the seismicity. We mapped out the active faults. We mapped out the relationships between the earthquakes and the volcanic features that were in Bob Christiansen's work. And that then turned us into, let's get a permanent network. Well, the USGS installed a permanent network in '73. They gave it up in 1980 and said to me, Bob, you take over the Yellowstone network. You have the drive and the interest. I says, I'll take it over if I can grow it to my own dimensions and reliability. Yellowstone operations are not California operations. It costs a lot more to have reliable equipment, and they agreed to and paid for it. We expanded the Yellowstone network then in the 80s, and then in the late 80s, GPS started to come in, and so we started doing portable GPS studies, integrating the two right here. University of Utah is the base of operations for all of the Yellowstone earthquake and volcano or deformation monitoring. That's an important feature that Bob Christiansen has always said, and it's true. So we had all these data coming in together, and then we began to evolve, modernize as more and more digital equipment came in, as bigger and better computers have come in, bigger and better databases have come in. And so that came up through the 80s. I had funding from the NSF to start the GPS, NSF funding to start the seismic, got USGS funding. We upgraded the seismic network. Park Service has always been very, very helpful with us, providing us all kinds of logistical support.
How is new technology helping to conduct Earth science?
Well, certainly when I first began studying in Yellowstone, the instrumentation, for example, the seismographs were very crude. They were recording on paper, smoked paper drums or in ink drums. We had no GPS. The actual sensors were very low magnification, would only detect relatively moderate to large earthquakes. Well, and it's because of computational methodologies. The whole area of seismic monitoring has evolved greatly, so that currently we have seismographs that are now capable of magnifying ground motion from as small as a magnitude 0 earthquake to a magnitude 8 earthquake and remain on scale. Space technology came in the mid-'80s. We have GPS, so we're using GPS to actually measure a point on the ground, and if we measure it with time, it represents ground motion, and so it's just like a seismograph. And so these new technologies, primarily of GPS and high quality broadband seismology that we received funding, by the way, from the ARA support of the USGS to upgrade to our newest system. We now have in Yellowstone a network of about 39 seismographs putting out 100 channels of real-time data and about 25 GPS systems putting out 60 or 70 channels of real-time data. All of the data are recorded digitally. That means they have high fidelity, they're very reliable, but they're in real time. That means they get to my laboratory here at the University of Utah the same time that it gets anywhere on the web. So anybody can have access to our data anytime they want.
Describe your collaboration with Bob Christiansen.
Bob and I worked together for years, very closely. I would spin off geophysical findings, he would spin off geological findings, and how they fit was uncanny, amazing. I mean, we would say, so he'd something about a volcanic history of a flow, and I say, well, here's the gravity signature of that flow that tells us how deep it is. Or that the seismic data here tell you something about a fault that's there that you've got on your map. So I worked really close with Bob Christiansen, and his thoughts pervaded my basic interpretations. So I think his mapping, his ideas of the caldera formation, my ideas of the processes of the magma chamber, how they were formed, how big earthquakes occur and map out the faults that are related to the magma chamber, really fit together. I worked to a certain degree with Bob Fournier because I was bringing my information to bear on hydrothermal systems, geysers, hot springs, etc. So I got to know Bob very well, and I worked with Bob for several years, and I still am in touch with he and Bob Christiansen, and it's always been very rewarding to put our ideas together. You get a better solution. You get a broader solution to a problem. In the case of Yellowstone, when we bring the volcanologists together with the geophysicists, one can constrain the other data. The earthquake information can constrain the size of a magma body. The size of the magma body tells the volcanologist how much magma there is that could be exploded. It tells the geochemist what percent volume of melt to solid rock in case of a partial melt. These things are done by people working together and collaborating and talking to one another routinely. And that's the part that I would say in the last part of my career that's been so fun, because I learn new things all the time, and so productive.
How did road surveys help clarify the story?
I knew from the earthquake data, Yellowstone was really active. And you can continue measuring earthquakes. And I said to myself, what we ought to do is measure the ground motion. Well, back in the 70s, the only way you could do that is with leveling, that is engineering spirit leveling. And so we formed a team. It was funded by the USGS, and we had a leveling team came from a USGS topographic division, came out, and we began leveling. Now, before that, I went to the Washington archives and got the old benchmark descriptions when they built the roads in 1923. And we were going to the same benchmarks, same roads. We were halfway across Hayden Valley. And as you go along, you calculate, you're walking, so you can calculate what the elevation was of that mark in 23 and what it is today. And we got further and further, and we kept getting further and further apart in the numbers. And I finally got halfway, and I said to M. David Cummings, the surveyor, we've got a big problem. We've got to go back and resurvey this whole thing, because we're off 2 feet. He says, I'm not off 2 feet. I might be off 1 or 2 millimeters, but not 2 feet. We finished the survey, came back to the university. I spent an entire year and a PhD thesis trying to take these data and prove they were wrong. They weren't wrong. We had measured 750 millimeters of uplift, almost 1 full meter, between 1923 and 1976 in the middle of the caldera. That's when we discovered Yellowstone had this very, very high uplift rate. And it's because we were being very careful, we were scrutinizing the data. We worked very hard to prove it was wrong, and we couldn't.
And now you use GPS?
Now we use GPS, and we have 25 permanent GPS stations that we run in Yellowstone, plus we go back into areas of Yellowstone. Another 30 points are measured annually. We call them annual measurements to fill in, get more detail. But the GPS is now giving us full pictures of the whole caldera. And we're supplementing that now with INSAR, that is satellite radar information that actually can take a picture of the whole caldera, and you have a pass every 2 weeks, and the new Sentinel satellite's just going to come on board next month. For Yellowstone, we're going to be able to get a picture once every 2 weeks. The problem with the INSAR satellite is it measures the top of the ground. If there's snow, it measures the top of the snow. So it doesn't work in winter. And that's where the GPS is continuous. And our GPS receivers are now so accurate. They measure the height change within millimeters and the distance change within millimeters per year. That's the width of your thumb. It's an amazing technology, but they all have to be worked together. Like I said, INSAR, GPS, earthquake data, they have to be interpreted together. One constrains the other.
Describe how you work with a new generation of scientists like Jake Lowenstern.
He and other people of this next generation are going to use new techniques, I'm sure, build upon what we've done, and there'll be another generation after that, because science develops new things, and that's always guaranteed.
How does plate tectonics relate to Yellowstone?
One of the basics of plate tectonics are plumes. One of the four, your subduction zones, extension, strike slip, and plumes. Well, plumes, I said, that's what's happened at Yellowstone. So I made up some conceptual models for Yellowstone in 1969 of how a plume could come up and well magma up and give us the heat that we're seeing at Yellowstone as a hotspot. So I published that paper. I gave the oral version in 69, published it in 70. We first started published 71, 72, 73, 74. So we had it all down then. We didn't have the new tomography. We didn't have the new GPS. These were conceptual models that were based on earthquake distributions and topography and geology. So plate tectonics had a profound effect, and that's when I named it the Yellowstone hotspot, and that it was a mantle plume. I didn't say it was a deep mantle plume. I said it was a mantle plume. Now we know it's an upper mantle plume. It goes down to about the mid mantle.
How does Yellowstone volcanism compare to Hawaii?
The difference between Hawaii and Yellowstone are the following. The crustal structure of oceanic plates are much thinner and they're much younger. So the magmas that come up from the mantle have a much shorter distance to burn through and create the volcanoes. Moreover, the continental crust is much thicker, much older, and contains much larger components of silicic rocks. Old rocks, remnants of billions-year-old rocks. So when you heat those up, you not only bring up basalts in the mantle in turn burns the lower crust, mid-crust, where there's a lot of silicic material, you get rhyolites. So in the case of Yellowstone, the rocks that come out are rhyolitic. And they are they're the flows that we see in the Yellowstone Snake River Plain. They're followed by the primary basalts after the plate has moved over the hot spot. But the difference being, one is a ocean plate with pure basalt. One is a continental plate, big, thick, and cold, that mixes in the magma, adds in the silicic component that creates the rhyolites and the granites we see at the surface.
How does the University of Utah work with Yellowstone National Park?
The park interacts with us because all of the data we have here, we send back to them in real time. So they have access to all of our seismic data, our GPS data, just as fast as we have it. The park doesn't have professional seismologists or geodesists. So what they rely principally upon us for is a level is interpretation of the data. So what they call upon us is, what does this mean? What does this swarm of earthquakes mean? Where is it? And so we provide the basic data, the metadata, and then we, for the park, can then provide interpretational data and maps and create images for them of our data that they use for their own teaching and for their emergency management. So the very important issue in Yellowstone is public safety, and the Yellowstone Volcano Observatory is set up to provide data for public safety and management of hazard issues.
Talk about the more recent lava flows in Yellowstone National Park.
There's been about 50 or 60 post-caldera flows, dominantly of rhyolite. There were basalts. These are flows that come out not necessarily explosively or catastrophically. They may cover only 2 or 3 or 4 square miles. They are only a few hundred meters thick at most, and they generally don't leave the park. They don't leave the actual caldera or the volcanic plateau. So these are not deemed to be a national threat, but these are the types of features that have followed the super eruption of 640,000 years ago. Well, the youngest of these is 70,000 years at the south end of Yellowstone. It's called the Pitchstone Plateau Flow. And it is right at the very south edge, and it's a high piece of topography around the caldera rim. and that's the youngest, and we've seen nothing since then.
Any epiphanies related to Yellowstone National Park?
The occurrence of the Hebgen Lake earthquakes was an epiphany. The discovery of this gigantic uplift of the caldera to 1985, followed by an 86 earthquake swarm. Whoa, that was something that really got us tuned in. And then the Earth's caldera went down. 2010, it went back up again. We had an accelerated uplift from 2004 to 2010. Called it accelerated uplift. It was going up at, went up 25 centimeters, a quarter of a meter. You know, while you don't see it in your footsteps, you know those are rates that are higher than geologic rate. They're higher than faster than San Andreas Fault is loading. Now, this last week, we just discovered now, very carefully, that the caldera is now returning back to uplift, and it's going up at 40 centimeters a year. So we view this caldera as this living, breathing thing, and I argue that all these little earthquake swarms that we have going around are really just relief valves. If we have a lot of swarms, that tells us fluids are squirting out of the magma body, and if we keep having swarms and squirting out, we're fine. If we stop that process, this magma body is going to inflate and we could have an eruption. So keeping track closely of the GPS measured ground deformation with the seismic activity in the swarms is helping us to understand the state of the system in terms of its capability and its whether it's an imminent threat or not. And I've had epiphanies my whole damn career up there.
How else is this information shared?
I had an NSF-sponsored workshop on Yellowstone, and we had teachers K through 12. These people saw all the data. They took the data away to use as teaching. So what I do with my teaching and all the information I get, my books, my talks, I give all my figures away to teachers, to National Park Service rangers. We give everything we have to the Park Service interpreters who meet millions of people a year. So I view it as a multiplying factor. By doing this and providing it, I can multiply my thought, my idea, by thousands by giving this information out. And I see it come back years later all over the web of the idea and the map that I made that I gave to somebody and then gave it to somebody else and got passed around and used. So to me, that's what distribution of information is about. And that's what education bases itself on.
How has public interest in Yellowstone changed?
It was 2004 when the public became aware of Yellowstone globally. That's when the BBC produced the Supervolcano movie. And we were consultants, and that documentary was actually correct. It just took a very rare feature and made it assume it was imminently going to occur. Well, that brought alive the fact that Yellowstone is a geologic park. Before then, people didn't think of it. They thought it was a elk park and fish park and geyser park. Now people understand it's a geologic park, and now people are understanding not only that, it has a magma chamber and it has a plume, and it's a major element of plate tectonics. It's truly a living, breathing, shaking caldera. And this all comes back to the idea, what are the processes? What are the physics of the motions? What's the chemistry of the fluids? How do they work together?